This is kind of our last topic. It's really 2 chapters in the book, but we're going to kind of just do it together. And that is kind of an introduction to organic chemistry. What do we mean when we say that this chemistry we're going to talk about is organic? Have we ever done anything with organic chemistry before? What this means, what it is, what we're talking about it all here? What do you think? What does it mean when we describe something as organic?
Like six or some elements or something like that. Yeah,
that's true. So it's chemistry dealing with a few elements, but where does that come from? Like, why do we call that organic? Why does this small subset of molecules end up being called organic? You know?
Is it because it contains carbon?
It does contain carbon. That's true. But like, what makes that special? Why do we care about this as almost kind of a separate category of chemistry?
Aren't they the elements that like all living things are made of?
Right. So this is the chemistry of living things. So the chemist, not like biochemistry, like what is actually happening inside organisms, but these are the molecules that living things are made out of. And the reason it's separate is because we used to think, long time ago, that these two chemistries were not organic, which was the chemistry of living stuff, and inorganic, which was the chemistry of rocks and minerals. We used to think that those two were completely separate, that living things were so special and had a special kind of life force that the molecules that were contained inside living things could never be made outside of living things. And similarly, the molecules that we saw in rocks and minerals would never exist inside living things either. And now we know that's not really true. There's plenty of crossover in atoms and atom, whether it's in a rock or in a plant or in a person or whatever. So we know that's not exactly true. You can make organic things from inorganic things and vice versa. But we still kind of keep that classification because, as it turns out, the chemistry of these things is a little bit different. And it's actually really predictable compared to other things, which is why we often use it. So we're going to define organic chemistry. And I'm going to put this in quotes, the chemistry of life, because that's kind of where it comes from, but that's not really what we mean now. We're going to talk about it mostly as compounds made mostly of carbon and hydrogen and oxygen. So with other stuff, there's all kinds of other stuff in organic compounds too, nitrogen, sulfur, chlorine, bromine. We will actually end up seeing a bunch of different elements in here, but primarily these are going to be molecules based on carbon. The other new thing kind of about this is we're going to look at some much bigger molecules than we've dealt with in the past. The other molecules we've been looking at are really pretty small, you know, one kind of sulfur atom in the middle with some oxygens around it or something like that. Now we're going to look at some pretty bigger molecules with these long chains of carbons and that sort of thing. So let's first take a look at what kind of causes this particular structure and this particular way of looking at things and this particular reactivity. And that's the way that carbon reacts. So if we imagine a free atom by itself, how many valence electrons does that carbon atom have? 4. How do you know? Yeah, because it's in the 4th column. So it's got 4 valence electrons. We usually can draw those in dots like this around the atom. And that also tells us that it has 4 spaces, like 4 places that it wants something to connect. We'll make squares for that here. We talked about that a little bit in a previous chapter, that based on the number of valence electrons, they can have a certain number of connections. which means that carbon is likely to form 4 bonds. So in the simplest organic compound, carbon bonds with 4 hydrogen atoms. This is kind of more of a schematic than an actual reaction because you can't just have free carbon atoms and free hydrogen atoms. But we're going to kind of put it that way just to think about it. And so it'll bond 4 times. And we know that satisfies the octet rule in carbon. And this molecule is called methane. Methane is a gas at regular conditions. It's very common. It's made by bacterial processes. There's all kinds of it in the ground. There's all these methane vents. One of the big catastrophic things that's probably coming from global warming is the release of more and more methane from these vents as the ice melts, methane that had been trapped in these glaciers. And that's actually going to compound the effect because methane is a greenhouse gas as well, like carbon dioxide. All right, so that's our simplest organic compound, methane. Now the structure is a little different from how we might draw it in a simple Lewis structure there. If you look at the bonds here, it looks like it should be 90 degrees, like it's just a cross type shape. But that's not really what it is. It actually has a different geometry. So I'm going to open this program here. This is called Chem3D, and it allows us to draw some molecules here. So we're going to look at a methane. And so you're just going to kind of let that wobble back and forth there. And you see that it's actually not cross-shaped or T-shaped at all. If we move it around a little bit, you can see how if we look at it at one particular angle, kind of freeze it in the middle there, it kind of looks like a T. But the actual structure is really a 3-dimensional structure. And maybe it helps if we do this. I'm going to go all the way around. So this 3-dimensional structure is what happens when those 4 hydrogen atoms try to get as far away from each other as possible. Because if they take this orientation, you can see the angle when it comes around there, that's a larger than 90-degree angle. So because it's a larger than 90-degree angle, those hydrogen atoms are farther away from each other. And since electron clouds repel each other, that's a good thing. That helps it be more stable. So that's how we know that this isn't going to take that T shape, because this makes more sense. This makes the molecule more stable. It keeps the hydrogens further away from each other. And so this is the actual structure that it adopts. And the name of this structure is a tetrahedron. So I'm going to freeze this thing and kind of pull it back around if I can. I'm going to make it a little smaller so it fits in our notes. So there's our methane molecule. And so we can annotate this a little bit. We've got a carbon atom in the center and hydrogen atoms around the outside. And this is called a tetrahedron, or a tetrahedral geometry. The reason for that is that's named for the actual shape that this takes on. I'm going to make another copy of it here so we can look at that. If we connect the dots from the middle of each of these hydrogen atoms like this, And then there's kind of one that's going back like this too. I don't know if you can see that. She used a different color. But that is a shape known as a tetrahedron. It is a regular solid, which means it has the same, it has equilateral triangles on every face. Each face is the exact same as any other face. It has 4 sides or 4 faces and however many edges and 4 points. So that's the shape that it takes up with the carbon atom right in the middle, and that's called a tetrahedral shape or a tetrahedral geometry. The bond angles then in that geometry, so that bond angle is about 109 degrees, 110 degrees. So bigger than 90, and that's why this molecule takes that shape. And in fact, anytime we have a carbon in a structure that has 4 things attached to it like that, it's going to take on this shape. So that's why we spend some time looking at this particular geometry. Anytime we see any of these organic compounds, even with lots and lots of carbon atoms, the angles and the shapes that these compounds take relies on this particular geometry. It relies on that shape, that angle. And so we'll be seeing that. We'll be seeing that a lot. The way that we draw this in 2 dimensions, you might have seen it on my other program there, is like this. So we draw our carbon, and then you notice the one hydrogen's going up, and the other one's kind of going off to the side like that. Those 2 are in the plane of the screen there, meaning that they are like right at the same spot as the screen. But then if you remember from how the thing looked in 3 dimensions, the other 2 atoms on the right, one of them's kind of coming out at you and one of them's going back. So if we take a look at that again, see this one's coming out at you and this one's going back. See that? So these 2 are right in the plane, but the other ones are going out and coming back. So we have to find a way to express that. And the convention that we use is what we call dash wedge notation. This wedge, it's called the wedge, means that that hydrogen is coming out at you. And then we make a dashed line like this to show the other one going back away from you. So one of them's kind of going away, one of them's coming toward us. But actually those 2 are exactly in the same position, just kind of back and forth. We can't draw them right on top of each other, of course, because we couldn't see them. So we offset them a little bit. But really what we're trying to express there is this. That those 2, the things coming out and going back, are right on top of each other. And then we've got this thing coming up and this thing going off to the side in the plane of the board. All right, so there's our molecule. All right, so let's make a big molecule. We'll get into looking at this in a minute, but let's add a few more carbons here. Let's say we had a big chain of carbon atoms with hydrogens on them. So what I want, we'll talk about these big molecules in a little bit, but what I want you to notice here is that each of those individual carbon atoms actually has that same shape. You see that? The same kind of tetrahedral 3-dimensional shape. So that's going to control the shape of these larger molecules. In other words, if we have a compound that's a line of carbon atoms, it's not really a straight line. It's actually a zigzag because of that bond angle that these things take. Because of that 3-dimensional geometry, that chain of carbon atoms is really going to be a zigzag chain and not a straight chain. So keep that in mind, because now we're going to talk about some of these chains of carbon atoms, but we're going to draw them in a straight chain just because it's easier to see when we draw them that way. And that's not like just something we're doing for this class that's a common thing to do, is we express these structures in just 90-degree bond angles because it's easy to draw and easy to see. But we know in our head that really the structure looks more like that. Okay, so let's look at those. The first compounds we're going to look at, the simplest organic compounds, are called alkanes. Alkanes are compounds with just carbon and hydrogen and only single bonds. When we looked at the Lewis structures, we kind of talked about how you can sometimes have these multiple bonds between atoms. We'll get into that with organic compounds too. But this first category, all these structures just have carbon and hydrogen, and they're just made with single bonds. And one thing we're going to learn from these compounds is the basic names of the organic structures. Based on how many carbons there are, we give them different names. So we're going to make ourselves a little chart here. We've got the our formula, then our structure, and we'll leave a little room for this one because it's going to get a little big. Then we'll look at the name. And finally, what we call the condensed structure. As you'll see, these start to get a little bit tedious to draw when they get big. So there's all kinds of ways that we abbreviate these things to make them not as tedious. One of those ways is a condensed structure, and then a better one is a line structure, which we might get to later tonight. All right, so let's start from the beginning, the one we already know. The first one is CH4, and that's methane. And the structure, of course, we know now that the structure really is this tetrahedral structure, but we're going to draw it like this, a carbon atom with 4 hydrogen attached, and just kind of know in our brains that it's not really flat and T-shaped like that. The name for that one is methane. And its condensed structure also happens to be CH4. Pretty simple. Next one in the series is C2H6. Now C2H6 is going to look like this. And pretty soon you'll get the pattern down here and you'll be able to draw some of these. So we now have 2 carbons connected together and then hydrogens surrounding so that each carbon has 4 bonds. That one's name is ethane. And now we can see what a real condensed structure looks like. The condensed structure for ethane is going to be CH3, CH3. So let's take a look at what that condensed structure is, what that means. You can probably figure it out, but C2H6 is the molecular formula. That's kind of like how we've been looking at things so far. You count up the number of carbons and hydrogens and you just put them together, or whatever atoms are in there. With organic structures, that's not super useful because it doesn't tell us how things are connected. And as we'll see in a little bit, with some of these bigger molecules, there are several different possible ways they could be connected. So we need to be a little bit more specific. We could draw a structure and say exactly how it's connected. That's fine. But often it can be more convenient to write something like this. So this tells us we've got CH3, that's a carbon with 3 hydrogens on it, and then another CH3, another carbon with 3 hydrogens on it. In order for those condensed structures to work, we have to know a little something. We have to know that carbon has 4 bonds and hydrogen has 1 bond, because otherwise it kind of looks like you should draw a C and then H, 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 and then C and then H, H, H. The only way you would know not to do that is to know some things about these molecules and know that carbon has to have 4 bonds, hydrogen 1. So CH3 is going to be a carbon with 3 hydrogens on it, not a carbon and then 3 hydrogens connected in the row, because hydrogen only gets 1 bond. All right. The next member of the series is called propane. And its structure is C3, or its formula is C3H8. And see if you can draw the structure and the condensed structure for propane. So you need 3 carbons, 8 hydrogens. You're following the same pattern that we've done so far. And you need to make sure that carbon has 4 bonds and hydrogen has 1. Try to get something down even if you're not sure about it. All right, use something that looks like this. So watch how I draw this. I'm going to put my carbons in first. That's always a good idea when we start dealing with these things. We'll look at the carbon chain first, and then we'll fill in the hydrogens where they need to be. In this case, these carbons all need 4 bonds. So that's where we're going to put the hydrogens. And if that's a structure, how would you write a condensed structure? Condensed structures are kind of nice because you can say them also. You can read them across. What would yours look like?
CH3, CH2, CH3.
Yeah, right. Is that what other people got to? Yeah. Yeah, so you're looking at what's connected to each carbon as you go across. All right, the next member of the series, I'm going to give you the name. See, butane. See if you can come up with all the rest. The formula, the structure, the condensed structure. Probably want to do the structure first and then count up your carbons and hydrogens to get the formula. And then you can write the condensed structure also. And then if you finish that, see if you can do the final member of the series. Pentane. So if you're like me, you get kind of tired of writing those hydrogens over and over again by the time we get to these bigger structures. And this isn't even really that big yet. So you can see why things like these condensed structures can really help us out a lot. And there's actually a way to condense this even further. For these last two, another way to write this, look at this one first. This is the same as writing this. So you see what I did there? Those two repeating CH2s, I put them together with parentheses and a little 2 underneath them. So when you get really, really long chains, that can be helpful. Another way we can write this is CH3, and then 3 CH2s, and then CH3. So you can see that as well. All right, so that's a good start to our names, because now we know the names of these first 5 basic structures. And notice, and I was looking around when you were writing, most of you had no trouble coming up with these structures and these condensed formulas, which is great. So yeah, you do have to remember these names: methane, ethane, propane, butane, pentane. But you don't have to have a bunch of flashcards that say pentane is C5H12 and butane is C4H10 and has this structure. You can just figure it out. If you know that butane has 4 carbons, you can put those 4 carbons in a line, and then you can fill in all the rest of it and get the rest of it. And you all just did that, so you can definitely do that. Okay, rather than continue this on and on and on and on and on, let's grab this table from our book in chapter 11. So you can see some stuff about the properties and all that, and I'm just going to cut off part of this. Not that. So again, you know those structures. We don't need those structures, but it probably would be helpful. There we go. To have this kind of a table, so that you know the first 10 or so of these. Now we'll have to check Blackboard, but I believe it says there that you need to know those first 6. And that anything beyond there would be given to you. So know those names: methane, ethane, propane, butane, pentane, and hexane. Really the toughest ones are the first 4, because pent is something we're used to knowing with 5, and hex goes with 6, and then hept, oct, you can probably figure out the rest of them, but make sure you know those, because we'll use those in naming things when we get into that. All right, so we're going to stop there because this is a good stopping point. Take a little break. I'm going to grab some models, some chemical model kits, because we're going to play with that. And then we're going to, we'll meet back and we'll start talking about some isomers and some naming. So I'll see you in about 15 minutes. So we're going to look at something called isomers. Isomers are molecules with the same molecular formula, so like CXHY or whatever, C4H10, whatever it might be. But different connectivity, meaning they're connected in different ways. So take your models out, and we're going to build a butane molecule. Just one between every two people is fine if you're working with somebody. The black little shapes here are generally carbon. If you don't have enough black shapes, the red or green or blue will work fine too. These weirdly shaped ones and these gray ones with like extra holes in them, or other weirdly shaped gray ones, stay away from those. I think all the kits should have at least 4 black ones in there. And what you're going to do is use these little sticks as bonds and connect 4 carbons in a row to make butane. And then what I like to do is just leave a bunch of sticks sticking out of all the rest of the holes, and those will be your hydrogens. So you've got your basic core of 4 carbons, and then you're going to stick the sticks in all the remaining holes so that you can see where the hydrogens will be. If you really want to be fancy, you can put those little round balls on for hydrogens, but you don't need to do that.
Butane?
Yeah, butane, so 4 of them.
All right.
So something like that. It doesn't matter if the sticks are all the same size or what. Maybe stay away from the curved sticks, but other than that, it's fine. And you should see that it has that kind of angled shape like we saw in the modeling program before, because these little balls are also tetrahedral geometry. So everything's going out at the right angles. And you show something like that. Right here. Really nice.
Too easy.
The third exam will mostly just be building things out of.
Really?
No.
Oh my gosh, we're loving my day.
Sorry. All right, so you got your butane molecule. You got it. Now there is one other molecule that also has the formula C4H10, but it's connected in a different way. So let's draw what we just made. Now I'm going to use some colors here so that we can see it. We're going to keep things in a straight line, even though we know that's not really what it looks like. And I'm going to keep the carbon chains in blue and then put the hydrogens around them in red, just so we can see the carbon chain. So one thing that we might have to do is figure out what are these different structures that have the same formula that are connected in different ways. What are the isomers? What are their structures? If you're just looking at it on paper, it's easy to get fooled into picking one that looks different but is actually the same. So let me show you one of these. Let's say instead of having the 4 carbons in a line, we have 3 carbons and then 1 going down. And then we fill in the hydrogens around. So now we have to ask ourselves, is that the same or is that actually different? Is it an isomer? Does it have different connectivity? Or is it just the same molecule drawn a different way? The way we can answer it is with the models, until we get good at kind of doing this in our head. If you try to make a model of the one on the right, it just kind of maybe means twisting this around a little bit, but you're not changing anything. Everything's still connected in the same way. So the fact that we can't make a different model of that second structure means that these two are the same. They are not isomers. Isomers would require that we actually take this model that we built apart and build it in a new way. So here's how we're going to do that. We're going to pull one of them off the end. I feel like I should be doing magic or something. It's not magic. I'm just actually going to do what I tell you. Maybe it would be better if there were magic. Maybe not any tricks. All right, so I took that off. I'm going to put it, I encourage you to do the same, put it on the middle, on one of the middle sticks. So you have something that kind of looks like this. Now we didn't eliminate or add anything. We still have 4 carbons, and if we count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And now let's try to draw this structure and see how it looks. So something like that. All right, so if you have that built, and then you draw that structure, think about it, look at your structure, take a minute to just kind of stare at what you've drawn and at your structure, and convince yourself that that's what we drew, or what you drew actually is the same as what you built. But those are the same thing. So try to like line it up. So okay, this goes here, this goes here. So it's important that we get used to in our mind making this connection, this transformation between a 3-dimensional structure that we hold and a 2-dimensional structure on paper. Now that is an isomer. So these two are isomers. They have the same formula. They're both C4H10, but they're connected in totally different ways. The only way you can make one from the other is by ripping apart a carbon and sticking it on somewhere else. If you flip or if you twist or do any of that kind of stuff, that's not isomers. That's just flipping and twisting the same thing over again. So let's try this now. A little bit bigger structure. Pentane, 5 carbons. So we're going to get an extra piece there out of the kit. So pentane has 3 isomers. 3 different molecules that are all made of the same number of carbons and hydrogens. If we go back up to our chart, we see that pentane is C5H12. One isomer we already drew. It's the one where there's all in a line. So see if you and your partner can find the other two, either by messing with the balls and sticks or by drawing it. If you draw it, make sure that you can build it too, and that it's actually different. So this time you'll need 5 of the black pieces and a few more sticks. If you need to start combining with someone, that's fine too. I'll draw the first isomer, the one we already did. And then when you think you found a second or third one, come up and draw it for us. And we'll see if we can get them, even if you're not sure if it's right or if it's different. And then we will evaluate them together.
Is this one?
Come draw it. We'll see.
I'm gonna draw this.
We'll see if you can. So hold it in a particular way that you think might allow you to draw how it's connected. Connect the carbons first and then fill in the hydrogens around. You don't have to draw it in like some fancy 3D way. Just make sure everything's connected in the same way.
Draw it.
Yeah. We can draw on paper first if you want, and then bring it up here. But yeah, ultimately we want to see them up here. Go ahead. Sorry. Okay.
Ready to change color? Should I try now?
It's hard when you get to the edge.
Yeah, I forgot to drop text there. Okay, can I go back to blue?
Yeah.
All right, there we go. Just rough. There you go.
Thanks. Sounds good. All right, so hang on a sec. We have one structure up here. Is that one an isomer, or is it just another way of drawing the same thing? It's an isomer. Did you all find that one? Some people find that one? You found a different one? What?
So it's harder to draw than anything.
Yeah, it is. It takes a little getting used to. Yes, that is an isomer. One other way that you can tell, and we'll use this in a little bit later when we talk about naming, is try to find the longest chain, the longest continuous chain of carbons. Like in this structure, you can go 1, 2, 3, 4, 5. But in this structure, the longest chain you can get is 1, 2, 3, 4, or maybe 1, 2, 3, 4. But either way, you can't get that line of 5 carbons anymore. So that tells you it must be different. Now, when we get into these bigger structures, that's not always going to work, but that's a good kind of first approximation. All right, so does anybody have another structure that's not one of these two?
I do.
Yeah? You want to draw it? Thanks.
Is it here?
Yeah,
Okay.
and you can touch it. It's not a touch screen or anything, so you can like rest your hand on it.
Oh,
while you
okay.
write.
Oh, you can touch it?
Yeah.
Oh,
So no, it's not a touch screen. It only works with the pen.
I have another one.
Right, so I mean, she's.
Thanks. So you have a fourth one?
Yeah, but it's big as T. Like C, 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 C. And then mine's had another C underneath. So I consider it like-
But you think it's different from these three? Or you think it's one of those? It's the same as one of these? Or do you think it's different? I don't know. Come on, draw it.
True, right?
I didn't do it with the pretty color, I didn't know.
That's fine.
Okay.
Happy.
Yeah, draw it and see.
Can't be aligned. So just like this.
It's not a nice word, it's connected, it's what you add another one. Is that it's not, it's breaking the line. It's gonna just keep going, it's gonna be
Yeah, it's been.
Should have brought flyers to get these things out.
That's what I'm.
Oh yeah, is it? Are they stuck?
Awful. Okay.
Sorry.
Good.
Get a bunch of like Pop-Tart on your finger and it'll come off easily. Like the glaze, get your finger off sugary. All right, so you got some different structures here. Now I said there were 3 different isomers, but we've got 4 structures. So now we have to ask ourselves, are they all actually different isomers? Or are 2 of them the same? They're clearly all drawn differently. They look, like when we just look at them, they look different. Are they all different or not? What do you think? Let's look at that one in the middle first. What do you think about that one in the middle? Is that the same as one of the ones on the left, or is that a different structure? It's a different structure. It is. That's true. How do you know?
They're not aligned. It's not like the line doesn't continue, it's broken apart, so that's why it's on.
Yeah, it's broken apart a lot. So like the longest continuous chain you can count is 1, 2, 3 carbons, or 1, 2, 3, or 1, 2, 3. No matter where you start, if you're trying to count like continuous carbons, that is carbons connected to each other, you can only get to 3. Whereas here we could do 5, and here we could do 4. So that tells us it must be different. We can also look at the environments of the carbon. Like in this structure, we have a CH3 on the end and a CH3 on the end, and then 3 CH2s in the middle. In this one, we have 3 CH3s, a CH2, and a CH. In this one, we have 4 CH3s and a C with no H's on it. So if we have some really different environments like that, that's another sign that these are isomers. So to help with that, sometimes rather than draw it like this, it can actually help to draw it in the condensed structure. The only caution with that is make sure that your carbons still have 4 bonds, because it's really easy to accidentally draw a CH3 right in the middle of a chain and have a carbon with more than 4 bonds when you're using the condensed structure. So this one here is going to be, let's see if I can fit it in here somewhere. And with the condensed structure, another thing we didn't say before, you can draw it with lines or without lines. Whoops, and there I just made a mistake. Those should be CH2s in the middle. So I can put the lines there, or I can just draw them all smashed together like we did in that table. So that's that one. This one down here is going to look like this. And then this one here like that. All right, so let's look at this this fourth structure. Oops, I'm going to put that in my condensed structure also. So would you say that that one is a fourth isomer, a different isomer, or is it the same as one of these other ones?
It's the same.
It's the same as what?
The bottom left one to
The bottom left one?
the bottom.
Yeah, these two are actually the same. Let's think about how we would know that. Well, one way you could do it is try to build the model. You could build the model of one of them and then see if you could get it into a position so it looks like the other one. And you could actually just by rotating it. So if I grab one more, I can show you that. All right. So here's, let's say I build the, let's say I build the one over here on the left. You see that, my model there? Now I want to make it look like this one without breaking anything apart. So I can kind of just turn it up like this and kind of move this tail down, and then I've got that one. Does everybody see that? I didn't break anything apart, and I was able to make it look the same. So that's a sign that those are the same. Those have to be the same. So that's one way to do it. It takes a little while because you got to build model and stuff. Another way to do it is to look at the structure itself, to think about how to describe it. You could say, well, okay, this one has a CH with 2 CH3s coming off of it, and then CH2, CH3 on the other side. And this one also has CH with 2 CH3s coming off of it, and then a CH2, CH3. So there's no like official way to, you know, like an official procedure to say this is how you figure out that this one is the same as this one. Use your own judgment in terms of how you would describe something, and then can you see those other things as being similar? So these are the same, which means there are just 3 isomers. We're going to get a chance to practice this a little bit more, but before we do that, I want to look at the names, because this is another way that will actually help us to determine whether or not these are the same. So we're going to name the alkanes. As we did with the other compounds, the inorganic naming, the same kind of idea. Originally, every new compound was just given its name based on what it came from or what it smelled like or where it was discovered or who discovered it. And so you had to just kind of remember this huge list of names. And instead, people decided, well, we should just have a systematic way. We should have rules that as long as you follow the rules, everybody will always get the same name every time. And that's what we've done for our inorganic compounds. That's what we're going to do for our organic compounds as well. The rule for naming compounds, I'm going to write the 3 rules, and then we're going to try it on some of the structures that we've just done. So the first rule, and this is actually usually one of the toughest parts, find the longest continuous carbon chain. So you're going to look at your structure and figure out what is the most carbons in a row, just like we were doing before. Can you make 5 in a row? Is it 4 in a row? Is it 10 in a row? What's the longest chain before you have to kind of pick up your pen and go somewhere else? Yeah.
So you're talking about like 3 different names for like those 3 different isomers?
Right.
Names?
Right.
Okay.
So those 3 different isomers will need to have different names. Now the old-fashioned, as long as we're talking about this, the old-fashioned way was the straight one would be called pentane. Then one of them would be called isopentane, and the other one would be called neopentane. And those words sometimes still get used, but there's always this question of like, well, which one's which? It doesn't make any sense. So we're gonna use a better way. We're gonna use a way where there's only one name per molecule, and it's clear which one's which. We're gonna find the longest continuous carbon chain. Let's try it. Let's use one of our isomers from before here. And what is the longest continuous carbon chain in that structure? How many carbons? 4. There's 4 in a row. Everybody see that? You can't get more than 4 because you can't get that 5th one without picking up your pen or retracing your steps. So you got 4 carbons. What is a 4-carbon molecule known as? Do you remember from the table before? A chain of 4 carbons always takes the same name, and it's butane. So that means that our name of our alkane is going to end with butane. So let's write butane from that 4-carbon thing that we drew. So that's the first thing. You figure out the longest chain, and you can just write that down. That's going to be the last part of your name, the end of the name. Second part is we're going to number the carbons of that longest chain and I'm going to use a new word here. Talk about it in a second. So that the substituents are closest to 1, to number 1. Substituents mean things hang off, things that are not a part of the chain. The other stuff, the stuff that is substituted. So our longest continuous carbon chain is this one, right? We could also have picked this one. Shouldn't matter. If you pick the longest one, you should always get the same name, whichever longest chain you pick. So let's pick this one just because it's a little weirder. Not quite as obvious as the one that's straight ahead. But we should get the same thing as if we would have picked the straight ahead one, the left to right. All right, so there's our longest chain. Now we're going to number the carbons so that the substituents are closest to 1. What that means is this thing over here is considered a substituent because it's not a part of the main chain. So anything that's not a part of the main chain is a substituent. And if we want that one closest to 1, that means we've got to start numbering down here, not over here. We can always pick whichever end we want to start numbering at. We want to pick the end that makes the substituents closest to 1. So that means I'm going to pick down here to start my numbering instead of over here. And I'm going to go 1, 2, 3, 4. The last part of the name then is going to be We're going to find all the substituents and name them with the number that they attach to. Now to do this, we need to know something about substituents. So first we can find them. That's easy with this one. There's only one. There's our substituent. But substituents get named a little bit differently. So let's talk about them. If we have a CH3 that's coming off of some other chain, a CH3 substituent, that has the name of methyl, meth and then YL, methyl. A CH4 molecule would be methane. But this isn't a CH4 molecule. It's a CH3 that's hanging off of something else. So we call it methyl. You could probably see where this is going, but if you had a 2-carbon substituent, that would be known as ethyl. If you had a 3-carbon substituent, that would be known as propyl, etc. So we use that same base of that name, but we put YL at the end to show that one hydrogen is missing and it's connecting to a chain. So which number, back to our molecule here, that purple surrounded substituent is going to be a methyl substituent. Which carbon of the chain is it connected to? 2. So we would name that substituent as 2-methyl. And that name goes right up against the chain. So the name of this molecule is 2-methylbutane. Tells us everything we need to know. Tells us that we have a 4-carbon chain. That's what the butane tells us. And it tells us there's a 1-carbon substituent coming off of the 2nd carbon of the chain. And so we can draw that. We can have somebody else name it. Anybody should always come up with that same name. If we started our chain as being this one instead, straight across, we get the same thing. Because now this one is the substituent, and that would be 2-methyl also. So we'd still get 2-methylbutane. So the idea of these names is that they are unique, that only one molecule could possibly have the name. All right, let's try the other one that we drew, the other isomer of pentane. Let's use the same procedure. And then I'll show you how our name changes a little bit in this case. What is the longest continuous carbon chain? How many? 3. Which 3 do you want to pick? It shouldn't matter, right? So we'll just take the middle one because it's easy. All right. So there's our longest continuous carbon chain. Which means what's the end of this name? Propane. Good. Okay. Now let's find our substituents. We got this one. Oh wait, we didn't number yet. Let's number. So does it matter which end we start at, the left or the right? It doesn't, because the substituents are right in the middle. So we go 1, 2, 3. And then we've got substituent here and a substituent here. Now, this is a common mistake. 2 different CH3 is not an ethyl substituent. That's 2 different methyl substituents because they're not hooked together. To get ethyl, we need a CH2, CH3. So for the 2 different methyl ones, the way that we write that, instead of saying 2-methyl, we say 2, 2, dimethyl. Di meaning 2 of them. If there were 3, we'd say trimethyl. If there were 4, we'd say tetramethyl. So just like in the other names when you use those prefixes. So this molecule would be 2,2 dimethylpropane. We'd say that 2,2-dimethylpropane.
Is the 2,2 just because they're connected to?
That's right. So each substituent gets its own number, even if they're on the same carbon. So it's 2,2 because one of those 2's is for one of them and one of the 2's is for the other one. Doesn't matter which one's which, but you've got to have them, they both have to have their own numbers. So that's why 2,2. All right, let's keep trying this. Let's keep working on this. Let's try to find and name isomers of hexane. Now this is going to get a little bit trickier because there's more of them. I guess trickier and easier because there's more of them, but it's hard to get all of them. We're going to try to find all the isomers of hexane. That's molecules that have the formula C6H14. And use whatever procedures, you can use your models, work together. When you think you have an isomer of hexane, come put it up here, and then once we've got a handful of them, we will try to name them. As you see them coming up, if you want to try to name them on your own, that would be good too. See if you can come up with some isomers of hexane. And I'm not even going to start you, so there should be one pretty obvious one to start with. Are you looking up isomers of hexane?
Oh.
That's fine. I just
I don't
I just had to think about it instead.
Yeah, well, there's one more good thing. There you go. This one.
Would that be the same thing as well?
Oh, 6. 6. Oh, beautiful.
I see lots of good isomers. Somebody come post some up here so we can all see them. Oh, yeah, these are really good too. Does anybody have one of those like pocket multi-tool things with little players in them?
These things work.
What's that?
These like little, they come in the thing, it's like a little piece of foam or rubber or something.
Oh, I see, okay. Some of them must not have that, 'cause this other one doesn't have it.
Comes off or nothing.
Yeah, that's good. Nobody's got anything? I've seen plenty of good ones. Somebody come just try. Okay. Good. Yeah. Thanks. Let's get a couple more. So take a look at the ones that you've drawn, and if you got this one, put a little check by it. If you didn't, add it to your list, and think about whether the ones that you have there are the same or different. Couple more? Thank you.
Yeah.
There have to be some more out there. Yeah. All right. Thanks. Thanks. All right, we're getting pretty close. I'll do one, and then I want somebody to find the last one.
Oh, we take the CHM.
All right, I think there's one more. Unless I'm forgetting some. Yeah, there should be one more. I think I saw it on somebody's paper. Do you have one that looks different from that? You do, come put it up. I'll space these out a little bit too so we can do the names. One more. Why don't we do this? Let's look at the names. Does anybody think they have it? Maybe? All right, well, let's look at the names, and we'll see. Maybe that will help lead you to what it might be. All right, so we don't have the rules on the screen, but if you still got them on your notes or something, pull those up. We'll start with the one on the right, because it's easy. What's the longest chain there? 6, right? And what's the name of 6? Hexane. And does this have any substituents? It doesn't. Everything is a member of that chain. So we just number from 1 to 6, and that's it. That's the whole name. So that's just hexane. All right. Let's look at this one, the first one here on the left then. What's the longest chain there? 5. Does it matter if we start numbering from the left or the right? No, because that one's in the middle. So we'll just go 1, 2, 3, 4, 5, and that gives us what? Pentane. Right, 5 carbons is pentane. So then our substituent is here. So there's our longest chain. Our substituent is there, and what kind of a substituent is that? That's methyl, and what carbon is it on? 3, so that's going to be 3 methylpentane. See if you can come up with the names for these next two using those same rules. You want to give me a name for the second one? Yeah, dimethylbutane. One thing that we have to add in there is the numbering. So it's 2, 2.
I didn't know if you wanted me to say that, so I didn't say that for you.
Yeah. 2, 2 dimethylbutane. So our main chain is that butane, the 4 carbons across. And we have to start numbering from the right so that the substituents are on the lowest possible number. Both of those methyl groups are on carbon 2, so that's 2 and 2 dimethylbutane. And what about this last one? Did we get a name for that one? Yeah, this one's going to also be a dimethylbutane, but the methyl groups are on 2 and 3. So we actually keep the name very similar, we just change the numbers. This one's going to be 2,3 dimethylbutane. So we've got 2,2 dimethylbutane and 2,3 dimethylbutane. Anybody find that last isomer that we're missing yet? You think so? What would its name be? Okay. So naming actually becomes a powerful way to figure out this isomer problem too. Because if two things are isomers, then they have to have different names. But if they're the same, then they should have the same name. So even if it looks all crazy and you can't tell if they're the same or not, if you can use those rules to name them, and the name comes out the same, you know they're actually the same. If the name comes out different, then you know they're actually isomers. So naming, if you can do it, ends up being the best way to check that.
I'm sorry, why did you name methods again for the second one?
Yeah, because the second rule says number the carbons so that the substituents are closest to 1. Yeah. So if we named it the other way, it would be 3,3-dimethylbutane. And we always want those numbers to be as low as possible. Okay.
Is it 2-methylbutane?
Yes. No. Close. So you got the right structure? Not the right name. But I'm going to draw it exactly as you did, so we can see that. All right, so we got another structure here. I'll just draw it. Oh, wait, no, okay, well, we can look at this one anyway. So this structure, is this the same or is this different? So it looks like another, is this what you wrote?
Yeah.
So it looks like, okay, we're going to call this main chain right here. That's butane. So this looks like 2-ethylbutane, which is a different name from what we've seen so far. So is it different or not? Sounds different from the name. Unfortunately, that's not the right name. Why isn't it the right name? What's the longest continuous carbon chain here? Are you sure?
5.
5. There's a way you can get 5, right? If you go like this, you can get 5. 5 is longer than 4. So this is actually pentane. And what is that substituent on? Which carbon is the substituent on of that chain? 3. So this is another 3-methylpentane, the same as this one. Drawn pretty differently, but if we're really careful with those naming rules, we actually find the longest continuous chain, no matter how it's drawn, we find that we have the same name, 3-methylpentane again. So that's not an isomer, that's going to be the same. All right, so here's the isomer. Here's the last one that we didn't get. It looks like this. What's the name of that one? Right, this one is 2-methylpentane. So those are the 5 isomers. So now one other thing that we should know about with alkanes are these cycloalkanes. Cycloalkanes are carbon and hydrogen that end up in a circle or a closed loop. The smallest cycloalkane is this one. And this is called this one's called cyclopropane. So you can probably figure out where that name comes from. It's got 3 carbons, which is propane, and then they're in a ring connected to each other in a closed ring, closed loop. So that's called cyclopropane, and that's how we differentiate it from regular propane. When we just say propane, we're talking about a chain of 3. When we talk about cyclopropane, we're talking about a ring of 3. So we can keep doing this. Now, interestingly, this structure, what did we say the bond angles were in methane or any of these carbon compounds? About 109, 110, right? What's the angle inside of a triangle? Anybody remember from geometry class? Somebody said it. 60, yeah. Yeah, in an equilateral triangle, it's a 60-degree angle. So you've got a carbon bond that wants to be at 110 and is actually at 60. So what do you think's happening there? Probably not super stable. In fact, if you try to make a cyclopropane with your models, you'll break it because you can actually feel that you have to strain those bonds to push in at that angle. And that means that these molecules are pretty reactive because they want to break open. They don't want to be contained in that. Now, as we get bigger, they get more stable and they get more like regular bond angles. So things like these 5 and 6-membered rings so we've got cyclopentane, cyclohexane. Those are very stable, and these are These are structures that we see all over naturally occurring molecules, whether they're biological molecules or things like pharmaceuticals that we make to interact with biological molecules. A lot of these ring-type structures in them. Sugars and lots of other biological molecules like that use these types of structures, steroids and hormones and things like that. To name things with cycloalkanes is really the exact same, but the cycloalkane becomes the parent instead of the, or becomes the main name instead of just the alkane. So let me give you an example of that. Let's look at this structure. So we're going to use the rules the same way. The only difference is the numbering can be a little tougher because of the ring. So our longest continuous chain now, we can't really say chain because it doesn't make sense because you can go around a ring as many times as you want and just keep going, going, and going. So our longest continuous chain is really our ring, or the thing that we're going to base the name on is going to be this ring. So that's going to be, I'll do it below so it makes more sense here. That's going to be cyclohexane. We got to remember to put that cyclo in there, or somebody's going to think that you're actually talking about a straight chain. Remember that these names are all about communication. When you write a name down, it's so someone else can then draw the structure and know what kind of structure you're talking about. So we have to be really, that's why they're kind of like nitpicky rules. They have to be precise, or you end up writing down the wrong structure. All right, so that means that our substituents are here, here, and here. How are we going to number around that ring? Does it matter where we start with 1? What's going to control that? How do we decide where to put 1? When we were looking at chains, our rule was to number so that the substituents are closest to 1. That's still the rule. But with rings, maybe a better way to phrase that is that we want the lowest possible numbers for the substituents. And this is kind of going to be trial and error then. So we're going to number them a few different ways and try to figure out what gets us the lowest numbers. We could probably figure out from that we want to start at one of the carbons that has a methyl group on it. So one of the methyl groups is going to be 1, right? Which one do you want to start at? The what? Lower left, so this one? Like that, 1. And then go up. So we got 1, 2, 3, 4, 5, 6. So that gets us 1, 2, 5 trimethyl. Can anybody think of a way to get lower numbers than that? You start down here. I'll use another color so we can see. And then go which way? Clockwise. So 1, 2, 3, 4, 5, 6. All right. So the first way got us, we should keep track of this. The red way got us 1, 2, 5. The blue way gets us 1, 3, 4. Upper left and go down. I run out of colors here. So 1, 2, 3, 4, 5, 6. That gets us 1, 2, 4. So what are the lowest possible numbers there? 1, 2, 4. So we're going to go 1, 2, 4. Trimethyl cyclohexane. And that's our name.
So if you were to like give the name of 1, 2, 5 and have somebody, like, would they draw the wrong thing? Or would they end up drawing the same thing?
Yeah, so in that case, it's really a convention thing, because you're right. 1, 2, 5, however you number it, you're going to draw the same structure. So you're going to draw the correct structure. So it's no longer an issue of uniqueness. But let's say you need to buy some of this stuff, so you want to look in a catalog. There needs to be one correct numbering that you look up so that everybody's talking about the same thing. And so the convention is just you want the lowest numbers possible. But you're right, you would still draw the correct structure with any of those numbering schemes. All right, let's try a couple more names and then call it a night. All right, so you can come up with some names for those two structures.
On that first one,
Yeah.
CH2.
Oh, yeah.
CH3, is that 1 or is that 2?
So 2. What do you mean?
Like, is that two different compounds, or is that just one long one?
It's one long one. I just took the line out of the middle. All of these, the lines are optional. So sometimes you'll see them with the line. Sometimes everything will just kind of be mashed together.
What lab are we doing this one to?
Oh yeah, Wednesday is the organic chemistry lab. Yeah, we're skipping over the nuclear one for now. We're gonna do that in a couple weeks because there's no lab next week. Anybody have some names yet? Maybe? Maybe not. Say that again, sorry.
Yeah.
3. Like that? Okay. What do you think about that name? Is that right? Did you get something different?
Well, isn't the longest one? Oh, sorry, I forgot the rest of the
Yeah, so the longest chain here is going to be this one, which is 5. And then we can number 1, 2, 3, 4, 5. So both of those methyl substituents are on carbon 3. So that's the only issue with this name is it should be each substituent needs its own number. So it should be 3, 3 dimethyl instead of just 3 dimethyl. But yeah, good. All right, who's got the next one? Three. Ethyl pentane. What do you think about that? Yeah? Yeah? Yep, I'm gonna agree with that one. Same thing, we got, this is our longest chain, that's 5, that's pentane. 1, 2, 3, 4, 5. Now there's only one substituent here because that CH2, CH3 is all coming off of the same spot on that same carbon. So this isn't a dimethyl thing. Those two carbons are part of the same substituent. So we have to think about them all together, which makes them an ethyl substituent instead of a methyl substituent, a 2-carbon piece. So that would be 3-ethyl pentane. So main things with naming, you got to know the names, first of all, the methane, ethane, propane, butane, pentane, hexane. Don't get tripped up with the finding the longest chain. That's a common problem is picking the wrong, just like picking the one that's in the middle instead of actually following it all around and figuring out what's the longest. And then make sure you're naming your substituents properly based on which carbon they are on. And that's naming. So Wednesday we'll have lab. We'll do deal with some organic reactions and compounds in lab. And then next week, Monday, we'll finish up this chapter, talk about line structures and reactions, and then get into some other types of organic compounds. And that'll be the end of the semester pretty much. So then it'll be exam and that's it.